try to stay presented, like I'm going to try to stay on this window because when I flip back and forth from the document camera to Google Meet, I know on your guys' end it gets kind of glitchy. So what I want to start looking at before we get into a lot of the calculations are just the definitions of acids and bases. So we're going way back to, video 1 and video 2, where we're looking at what is a strong acid, what is a weak acid. So just looking at the strong acids and strong bases, remember that there are 7 strong acids. So HCl, HBr, HI, HClO3, HClO4, HNO3, and H2SO4. If it's not one of the strong acids, it's weak. Strong bases, so it says group 1, metal hydroxides, and heavy group 2. If you remember, that's just the B on the periodic table. So if you think on the periodic table, you have, right, hydrogen. We don't worry about hydrogen, but we go lithium all the way down to francium. And then we have calcium all the way down as well. So it makes this lowercase b on the periodic table. So any of these metal cations with hydroxide, those are strong bases. So LiOH, NaOH, CaOH2, SrOH2. If it's not one of those strong bases, we assume it's weak. So now as we look at the definition, so we talked about 2 main definitions of acids and bases, and the first one was the Arrhenius definition of acids and bases. So the Arrhenius definition is really more based on the formula that we see. So an Arrhenius acid is a substance that increases the H+ ions or the hydronium ions. Something to keep in mind, right, for you guys is that H+ is the same thing as H3O+. So whether you write something as H+ or H3O+, they are the same. Whichever way you write it is up to you, but you need to know that if you see H3O+ given in a problem, it's the same thing as H+. So we tell that something is an acid by if it starts with an H. That's kind of the Arrhenius definition. If it starts with an H, it produces H+ in solution, and it's an acid. An Arrhenius base is a substance that increases the OH- concentration. So we look for OH- at the end of the formula. NaOH, CSOH, SrOH2, right? That's the definition of an Arrhenius acid and base. Now, we could look at how these dissociate, but we're going to actually focus on that more when we look at strong and weak acids. So we have Arrhenius acids, produce H+, Arrhenius bases, produce OH-. So the Arrhenius definition is somewhat useful, but there are some limitations to the Arrhenius definition. And so what we use and what College Board typically uses is the Bronsted-Lowry acid-base definitions. So this is where we're looking at protons. Remember when we talk about protons, we're talking about H+. So from now throughout acids and bases, a proton represents an H+ ion or H3O+ ion. So remember that a Bronsted-Lowry definition of an acid is a substance that donates a proton. Right? An acid has an H+ to donate. HCl has this acid or this proton to donate. H2SO4 has 2 H+ to donate. Even a weak acid, right? Even a weak acid like acetic acid, even though it's weak, it still has that H+ that it could donate. So the definition of an acid is that it donates a proton. The Bronsted-Lowry definition of a base is that it accepts a proton. So when you're looking at an acid-base reaction, you're looking from the left to the right, and you're seeing what has to happen for this reaction to occur. So for example, there are these sample, right, acid-base reactions, and it says write the reaction. So if you have to write the products, you want to look and see, okay, well, what is my acid, what is my base, and what would that mean? So HC2H3O2, that's acetic acid. More than likely in the prompt of the problem, it would say acetic acid. If it has acid in the name, it's an acid. And so that means that acetic acid will donate its H plus to water. And after acetic acid donates its H plus, it loses an H plus. So it becomes C2H3O2 minus, and water becomes H3O plus. So notice how acetic acid donated its H plus to water, became C2H3O2 and H3O plus. NH3, so somewhere, whether you're just writing all of this on a piece of paper or you're looking back at your notes, I want you to make yourself a note somewhere. NH3 is ammonia. NH3 is ammonia. Ammonia is a weak base. Ammonia is a very common weak base. So somewhere in your notes, make a note that ammonia, NH3, is a weak base. So if we know that ammonia is a weak base, that means it's going to actually donate an H plus, or it's going to, accept an H plus from water. So it's going to become NH4 plus because you're adding an H and a +1, and water is becoming OH minus. So in this is looking at how the proton is being donated or accepted. Acids always donate the proton, bases always accept the proton. Now, in this, notice how water can act as either an acid or as a base. That's because it's called amphoteric, right? And we'll look down at the bottom. We'll talk about the conjugate acids, conjugate bases in a second. So if we look at this, HCl plus NH3, well, you need to think and label everything. So always label every substance. If I think about it, okay, HCl, that's hydrochloric acid, that's a strong acid. NH3 is ammonia, that's a weak base. Now the strong and the weak doesn't really matter right now, but what matters is that we've now labeled what's the acid and what's the base. That tells us what donates the proton and what accepts the proton. So HCl donates the proton to NH3. So donates the proton to NH3, HCl becomes Cl minus, NH3 becomes NH4 plus. So now we've actually labeled, right, the acid and the base. Cl minus is what is produced after HCl loses an H plus. So this is the conjugate base, and NH4 plus is the conjugate acid. Now, based on this, these questions are asking us about how Cl minus compares to HCl. So on this side, notice how we labeled Cl minus a conjugate base. That means that Cl minus, if it's a base, is a proton acceptor. Think about, this is a double arrow. Think about what would happen if we went backwards. NH4 plus would donate its proton to Cl minus. Even though it's a conjugate base, it's still a base. Cl minus is still acting as a base here. So if HCl is an acid, Cl minus can act as a base. So you have an acid on one side, you have a base on the other, right? It's conjugate on the other side. Now, kind of taking this a step further with conjugate acids and bases. It's been a while since we've actually talked about these conjugate acids and bases. And so here it gives us this reaction again. It says Cl minus is called the conjugate base, right? So we've talked about conjugate bases. NH4 plus, right, we said is the conjugate acid. So remember that a conjugate base, so Cl minus, notice that Cl minus has one less proton than HCl. So a conjugate base has one less H plus than the acid. They only differ by one H plus, just one. Notice how NH4 plus has one more H plus than NH3. So the conjugate acid has one more H plus. So in any conjugate acid-base pair, they differ by only one H plus, only one. So here it says HC2H3O2 is an acid. What is its conjugate base? Well, remember that the conjugate base has one less H plus. The conjugate base is what is produced after the acid donates its H plus. So that means that the conjugate base is C2H3O2 minus. So when you're looking at conjugate acid-base pairs, I'm hoping that in a multiple choice or in a free response question, the conjugate acid-base pair questions can be easy questions for you. So they differ by just one H plus. Now water is unique. And you can actually see here H2O, NH3, and HSO4 minus can all act as an acid or as a base. They're called amphoteric or amphiprotic. When it can act as an acid or a base, it's called amphoteric. In order for something to be amphoteric, it needs to have an H that it could donate, but it also needs space for an H to be able to be accepted. So when we look at, for example, H2O, right, it needs a lone pair to accept an H. So water has lone pairs. It could accept an H. NH3. So if we look at NH3, it has an H that it can donate, but it also has a lone pair that will accept an H plus. And then HSO4 minus has an H that it could donate. And if it has a minus charge, that means that it can accept an H plus as well. So H2O, NH3, and HSO4 minus are all amphoteric. So the conjugate bases would have one less H plus. The conjugate acids would have one more H plus. So for example, H2O, the conjugate base of H2O, you remove an H plus, it becomes OH minus. So if H2O is the acid, OH minus is the conjugate base. But if H2O acts as a base, right, the conjugate acid is what happens after you accept an H plus. That's H3O plus. So now I do want to point out OH minus and H3O plus. This is not a conjugate acid-base pair. These differ by two H pluses. So OH minus and H3O plus are not a conjugate acid-base pair. H2O and OH minus is a pair. H2O and H3O plus is a pair. Now, the last thing I'm going to talk about with the strength of conjugate acid-base pairs. As we look at conjugate acid-base pairs, it's really important to remember the stronger the acid, the weaker the conjugate base. So the stronger the acid, the weaker the conjugate base. So if you have a list of 4 acids, and it asks which of the following is the weakest base, well, the stronger the acid, the weaker its conjugate base. So if we have HCl, HCl is a strong acid. Its conjugate base is Cl minus. This is why Cl minus is neutral. It's negligible in terms of acidity or basicity. Because HCl is a strong acid, Cl minus is neutral. Same thing like HBr, another strong acid. Br minus is neutral. So you have that strong neutral pair or weak pair. But you can compare the strengths of conjugate acid-base pairs, even if they're all weak. Right, we'll talk when we look at the weak acids and weak bases, how to look at strengths of weak acids. But just remember that the stronger the acid, the weaker the base. Or you could go the other way. the weaker the acid, the stronger the base. So they're like inversely related. Right? As one goes up, the other goes down in terms of strength. So what I want to look at before we kind of look at the definitions of strong and weak acids is I want to actually look at this sample multiple choice question. So all of these sample multiple choice questions are not in the review document. I just wrote them on a separate piece of paper because these are questions. I tried to use sample test questions or sample quiz questions to write these. So you won't find them in the review document. But if we take a look at this, all of the following can be Bronsted-Lowry bases, except, so before I look at figuring out my answer choices, I want to label this Bronsted-Lowry base. So a Bronsted-Lowry base, we know, is a proton acceptor. A Bronsted-Lowry base is a proton acceptor. So this is asking all of the following can accept a proton except which one? So remember, to accept a proton, the molecule needs lone pairs or a negative charge. So to accept a proton, the Lewis structure needs lone pairs, or we see it as a negative charge. So I see S2 minus, right? It has a negative charge. If I add an H plus to this, it becomes HS minus. That's a perfectly acceptable conjugate acid. So S2 minus, that could be one. Right, this is an except, all of the following except. So we're trying to find which one does not match. Well, we know that water can act as an acid or as a base. All right, so we know that's true. And the reason, again, is because H2O has a lone pair. So when it accepts a proton, right, an H plus comes up and is able to actually bond with these lone pairs to produce H3O plus. So water is one. Then we look at NH3. Right, so here's NH3. NH3 has this lone pair. So when we bring an H plus, it will actually bond. It'll actually look like this. Here's NH4 plus. Right, NH4 plus is a perfectly acceptable conjugate acid. Then we have NH4 plus. So I'm going to use this that I just drew. If you take a look here, nitrogen already has 4 bonds. In NH4 plus, nitrogen does not have any lone pairs to accept a proton. NH4 plus cannot accept a proton because that would create something that would look like this, NH5 2 plus. Nitrogen cannot have 5 bonds. Nitrogen can only have 4 bonds. So our answer for this is NH4 plus. So H2O, NH3, and S2 minus can all act as Bronsted-Lowry bases. NH4 plus cannot. So that's looking at a Bronsted-Lowry base sample multiple choice question. Before we move on to kind of the definition of strong acids and weak acids, are there any questions on looking at the conjugate acid-base pairs, amphoteric? Any questions on those? Okay, so then we will move on to look at the strength of acids and bases. So we're going to talk a little bit about a strong versus a weak acid. And then the rest of our time will be focused just on strong acids and strong bases. So remember that the strengths of acids and bases, just like any electrolyte, depends on how it dissociates in water. A strong acid completely ionizes in water. Right? It ionizes 100%. That's the definition of a strong acid. Something else that we can think about in terms of strong acids is that the more H plus we have, so the more H plus that is created when it ionizes in water, the stronger the acid. So when you're looking at, which of the following is the strongest acid, look at the one that creates the most H plus. So strong acids essentially go to completion. So equilibrium lies very far to the right? So it creates essentially all products. The value of Ka is very large, which is why we don't even see Ka values for strong acids, because it's such a large number. We have almost all products compared to reactants. So when we say essentially goes to completion, that's like HCl will ionize into H plus and Cl minus. We use a single arrow because we assume that essentially all of the HCl ionizes into H plus and Cl minus. So when we're looking at calculating pH, right, we can say that the concentration of the strong acid is actually equal to the concentration of H plus or H3O plus, because it completely breaks apart. It completely ionizes. A weak acid only partially ionizes, and it's at equilibrium. So when we think about a weak acid, I'm just going to use HA, right, kind of the shorthand. It's at equilibrium with its ions, H plus and A minus. And that A minus could be any conjugate base. But equilibrium actually lies to the left, which means that we have mostly what is on the left of the arrow. We have mostly weak acid molecules. Ka values are very small, because if you think about Ka, it's products over reactants. Right? We have mostly reactants, so it's going to have a small value of Ka. And when we think about calculating pH, because it's not at it doesn't go to completion, it's at equilibrium, we have to actually use Ka to figure out pH, which we'll do in the next session. So strong acid completely ionizes, weak acid does not. So that's why it's really important that we always label everything. And then remember, the more H plus that it creates when it's in solution, the stronger the acid. So I actually was getting some questions about how the strength of acids work, right? If a strong acid completely ionizes, what does that mean about the attraction between the ions? Well, if it's a strong acid, that means that it breaks apart easily. So this HA bond, right? So HCl or HBr or HI, that attraction between the ions is extremely weak. In a weak acid, the attraction between the H plus and whatever the conjugate base is, that attraction is actually really strong, which is why it only partially ionizes. So the strength between the ions actually can help us figure out if it's a strong acid or a weak acid. So that's just kind of thinking about it at the molecular level. So now what we're going to do is we're going to tie this back into particle diagrams. And we looked at particle diagrams a little bit in class, but I want to look at it a little bit more. And we're actually going to do some practice with these particle diagrams. So strong acids, again, notice the single arrow indicates that it completely ionizes. So the strong acid completely ionizes to create the ions in solution. You have your 7 strong acids, so any of these 7 strong acids will completely ionize. And we see that as a single arrow. Now, what it means in terms of a particle diagram is that if we have a strong acid and it completely ionizes, that means that at the particle level, we should see only H plus and Cl minus ions. So I'm going based off of this equation up here. We should only see H plus or H3O plus and Cl minus ions. So notice as soon as the HCl gets put into water, it immediately breaks up into H3O plus and Cl minus, because the definition of a strong acid is that it ionizes completely. Now the difference between that and a weak acid. So here we have HF. Right? Remember that HF is a weak acid. People always miss HF. HF is a weak acid. This is just showing some of the weak acids. Right? You assume that if it's not one of the 7 strong, that it's a weak acid. But because it's weak, it exists at equilibrium. So the equilibrium arrow tells us that it only partially ionizes. So if we think about what this means at the particle level, when we put HF into water, only some of the HF will ionize. So down here, notice that we only have a few H3O plus and F minus ions. The rest, so we have 1, 2, 3, 4, 5 HF molecules. So a majority of this HF exists still as the weak acid molecules. Only a couple of the HF, right? Only 2 of the HF molecules actually broke apart into ions. So weak acids only partially ionize. So at the particle level, we would actually expect to see more of the weak acid molecules than ions. So there's actually a particle diagram question because College Board loves asking particle diagram type questions. So you'll see if you have that review document open, this is on page 5. So a skill for the AP exam, which means a skill for all of our tests and quizzes, is looking at particle diagrams of acid strengths. So we consider 2 acids, right? A very strong acid like HCl and a weak acid like acetic acid. Right? Acetic acid is actually vinegar. So vinegar is a weak acid. So it says these acids are in water. When they dissociate, they produce H plus and then the anion. So either Cl minus or the acetate ion. So this is a practice question. In the boxes below, draw a diagram of the relative number of these species by representing them as dots. And so you can just use, H plus as a small dot, Cl minus as a big dot. You can color code them if you want. So I have different colored pens here. So I'm going to use these different colored pens to help draw the particle diagrams. So then it says in the space to the right, first write the dissociation equation using the correct arrows. So over here, right, I'm going to start by writing the dissociation equation. So HCl, right up above HCl, I'm going to label that a strong acid. I know that HCl is a strong acid. So what I'm going to do over here is I'm going to write HCl, and because it's a strong acid, it has a single arrow. Now, could you write HCl plus H2O? Yes. Or you can simplify it and just do HCl single arrow with the ions. Either way works. So because it's a strong acid, it completely ionizes into H plus and Cl minus. So here it says show 10 molecules. So I'm going to do, let's see, I'm going to use different colors here. I'll use pink. So I'm going to use this light pink for H plus, and I'm going to use green for Cl minus. So I did H plus as a small pink dot, Cl minus as a larger green dot. So this represents Cl minus. This little one represents H plus. So I'm keeping in mind that cations are smaller than anions. Now for showing 10 molecules. If I have 10 molecules of HCl, it's a single arrow. 10 molecules will completely break apart. All 10 molecules. I'm going to write that here. All 10 molecules will dissociate. Why? Because it's a strong acid. All 10 molecules will dissociate. So that means if I have 10 HCl's, I'm going to have 10 H pluses, and I'm going to have 10 Cl minuses. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, the reason I have 10 H pluses and 10 Cl minuses is because we think about stoic. If I have 10 HCl's, I had 10 H pluses and I had 10 Cl minuses. So if they break apart, I still have 10 H pluses and 10 Cl minuses. So now I'm going to draw my 10 Cl minuses. But notice how they're all dissociated. None of them are attached to the H pluses. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Doesn't matter where you draw. No, I'm just trying to space them all out. So there are 10 molecules of HCl. Strong acid means that all of them dissociated. This is actually why strong acids and strong bases are good conductors of electricity. They're strong electrolytes. They exist as all ions. So if this were NaOH, right, it'd be the same thing. We'd see 10 Na pluses and 10 OH minuses because it's a strong base. Now, the bottom here, right, we have acetic acid. So I'm going to start by labeling this a weak acid. Acetic acid is not one of the 7 strong acids, so it's weak. So I'm going to start by writing the dissociation equation over here to the side. Because it's a weak acid, it exists at equilibrium with its ions. Right? H plus C2H3O2 minus. So I'm going to say I'm going to simplify this. I'm going to simplify this a lot more. I'll use orange. So I have H plus. I'm going to use a large orange dot for acetate. So I'm really simplifying acetate to just be one dot. Right? So here's acetate. Here's H plus. So H plus is just a small blue dot. Acetate is a large orange dot. Now, if I have 10 molecules, this is a weak acid. Weak acids do not ionize very much. Right? Usually it's less than 5%. So I'm going to say only a couple weak acid molecules will ionize. Now I'm probably only going to show one ionizing because 1 of 10 is still 10%. And that's even probably more than what acetic acid would dissociate, would ionize. So I'm actually only going to show 1 of them dissociating because weak acids usually ionize less than 5%. So I'm going to show 1 acetic acid molecule ionized. So I'm showing 1 of them broken apart. Then I'm going to show the rest of them still together. I'm just doing all of my H's first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so I'm going to show all of these still together as molecules. And there we go. All right, so again, what I showed here is that we had 10 molecules of acetic acid. I only showed 1 of them. Only 1 HC2H3O2 ionized. That's still about 10%, which is still more than a weak acid would probably ionize. So this is going back to the fact that strong acids completely dissociate, which is why we can use the single arrow. Weak acids only partially dissociate, which is why they exist at equilibrium. So since they exist at equilibrium, we have to go through and use ice tables and everything like we did with weak acids. Any questions on what we did with these particle diagrams? Again, this is just trying to go back and kind of review some things that College Board will want us to look at with strong and weak acids. All right, so then we're going to get into calculations. So now we're going to get into calculations with pH. So just focusing on the pH scale. So we are now done with weak acids until the next session. Our entire focus now is strong acids and strong bases. So when we think about the pH scale, just some equations that are useful. So all of these, you can tell this is just a screenshot from your equation sheet. So these are all of the equations that you have on your equation sheet. pH is negative log of H plus, POH is negative log of OH minus, 14 is pH plus POH. All right, this is all assuming we're at 25 degrees Celsius. So this 14 equals pH plus POH is assuming we're at 25 degrees Celsius. When we think about pH, you have to make sure that you're paying attention to what you're taking the negative log of. And we're going to look at some examples. Just a quick reminder of sig figs, the number of significant figures in your given concentration. So like in this example up here, 1.0, that's 2 significant figures. That's the number of decimal places in pH. Because when you're taking the negative log, you're taking the logarithm, your sig figs become decimal places. Some things with looking at the pH scale down here. So remember your pH scale goes from 0 to 14, 0 to 7, right? The lower the pH, the more acidic. The higher the pH, the more basic. If you take a look at the H plus concentration, this is something that's useful to remember. Notice that up here, 10 to the 0 is 1, right? 10 to the negative 1, it's 0.1, 0.01, 0.001. So notice here, right, the more H plus, the more acidic. So notice up here, the more H plus, the more acidic it is, right? The less H plus, the more basic. Because pH is the negative log of H plus. So the more H plus you have, the more acidic something is. So you want to keep little things like this in mind. The more H plus we have, the more acidic something is. So if a question is asking, what has the highest concentration of H plus ions? Well, the highest concentration of H plus ions is the one that has the lowest pH. So as we look at just some practice with pH, again, if you have this review document open, these are on page 9, and we're not going to go through all of these, but this is just practice with the calculating pH from either just H plus or from a strong acid or from a strong base. So we'll work through a couple of these, and then we actually will do some sample multiple choice questions as well to kind of help with all of these. So when we look at, let's say we look at number 2, right? Up at the top, this is calculate the pH. Now, remember on your test, you will get a calculator. We'll work more on the mental math and the estimation when we're reviewing for the AP test. So it says that some you could do in your head. Those are ones like this, where you have a 1 in front of the multiplication symbol. But we'll work more with that as we review for the AP exam. So for number 2, right, we're just going to work through the ones that I starred on here. So for number 2, H plus concentration is 2.5 times 10 to the negative second. Well, our goal is to find pH. So for this, we're lucky we can just find it in one step, because pH is negative log of the H plus concentration. Now, what I recommend is that you practice doing this in your calculator, just so that if for some reason you can't figure it out, we can make sure that we get it figured out for you. So negative log of 2.5 E negative 2. Now, two significant figures were in the concentration, so 2 decimal places are given in the pH. So 1.60. So pH is 1.60. Now, remember that your pH should usually fall somewhere between 0 and 14 if we're at 25 degrees Celsius. Now, if we look at number 3, right? Number 3 says the concentration of HCl is 5 times 10 to the negative 4th. So the concentration of HCl is 5 times 10 to the negative 4th. Whenever you are given a substance, label it strong acid, strong base, weak base. If it's a salt, so if it's an ionic substance with a metal and a nonmetal, or a metal and a polyatomic ion, label it a salt. So for this, we have HCl. So it starts with H, so it's an acid. HCl is one of the 7 strong acids. Now, the reason that that's important is because if we have HCl, it's a single arrow. It completely ionizes into H plus and Cl minus, which means if we have 5 times 10 to the negative 4th HCl, this is a 1-to-1 ratio. So that means that we have 5 times 10 to the negative 4th H plus. Well, now we have H plus, so pH is just negative log of H plus. 5 times 10 to the negative 4th. So if in my calculator we do negative log 5 E negative 4, we get 3.30, because this was 2 significant figures. 3.30. And then we could answer, is this acidic or basic? Well, if it's a lower pH, it's going to be acidic. So when you have a strong acid, to be the same thing in number 4, you have a strong acid. It completely ionizes. So whatever your concentration of your strong acid is, that's also your concentration of H plus. Now let's move up to number 6. All right, we're just kind of skipping around on here doing some practice. We have OH minus. The goal is still to find the pH. So if the goal is still to find the pH, think about how you could solve this. And there's 2 ways. The way that I would recommend, that is probably a little bit easier, is finding the POH. So take the negative log of OH minus. So if I find the POH, negative log 3.5 E negative 2. So the POH, notice how I'm labeling everything over here. Label what you're finding, is 1.46. That's the POH. Well, then remember that pH plus POH is 14. You have this equation on your equation sheet. Right, that equation's on your equation sheet. So 14 minus 1.46. The pH is 12.54. Now, another way that you could do this is that you could solve for H plus. All right, so you could solve for H plus by remembering that H plus times OH minus is KW. And then once you solve for H plus, you could find the negative log. Right, and you would have gotten the same thing. So there were 2 different ways that you could solve this. Whichever way you pick is up to you. Now, I want to look at number 8. Right? I want to look at number 8. The reason, you'll see why I wanted to look at number 8 instead of number 7. But in number 8, we have CaOH2. We have calcium hydroxide. So I see OH as part of this substance. So that tells me it's probably a base. If I look at the periodic table, calcium is actually part of that lowercase b. So this is a strong base. So because this is a strong base, calcium hydroxide will dissociate completely, single arrow, into Ca2 plus and 2 OH minuses. 2 OH minuses. Right? The difference is that for NaOH, which is a strong base, right, NaOH dissociates into Na plus and OH minus. So for calcium hydroxide, I have 1 times 10 to the negative third molar calcium hydroxide. And because it is a strong base, it dissociates completely, you can just use your ratios. You can just stoich this. So I see that for every 1 calcium hydroxide, there's twice as much OH minus. So if you can't just look at this and be able to multiply, you can do this. For 1 CaOH2 produces 2 OH minus. Right? And then just do 1 times 10 to the negative third times 2. And we get 2 times 10 to the negative third. There's your OH minus concentration. For strong bases, you have to pay attention to the ratios. Right? Yes, NaOH is 1 to 1. But ones like calcium hydroxide, strontium hydroxide, barium hydroxide, they all have twice as many OH minuses. So then what you need to think about now, right? The goal is to calculate the pH. The goal for all of these is to calculate the pH. So then think about, okay, well, I have OH minus here. If I take the negative log of this value, if I take the negative log, right, I'm going to label this right up above. If I take the negative log of OH minus, what am I finding? Well, I'm finding the POH. So if I take the negative log of 2 times 10 to the negative third, again, I'm going to continue to label this POH just to make sure I don't get mixed up. 2.70, because 2.69897, right? 2 decimal places, it has to be 0.70. Here's POH. The goal is to find pH. So 14 minus 2.70, 14 minus 2.7, oops, is 11.30. There's our pH. Right, 11.30 is our pH. Which should make sense because, right, this is calcium hydroxide. It's a strong base. The pH should be above 7. So those are some practice questions with strong bases, right, or strong acids. So if this were something like HClO4, HBr, HI, right, any of the strong acids would be the same, right, where it dissociates completely and you're taking the concentration on looking for H+. If it's a base, you're looking for OH-, which means you'd find POH first. Okay, so let me scoot this up a little bit. Any questions on what we did here? Strong acids, strong bases. Okay, so then I have 3 practice questions here. And here's what I actually want to do. I'm going to give you guys a few minutes. And I'm going to kind of leave it like this. And I know you can't quite see the bottom yet. So I'll just give you a couple minutes and see if you can do questions 1 and 2 first. Right, questions 1 and 2 first. And then after just like a minute or 2, I'll scoot the paper up so you can see the bottom. But I want you to try these. So this first one, which solution has the highest concentration of hydronium ions? So keep in mind, hydronium ions is H3O+, which is the same as H+. And then which solution is the most basic? And then the pH of a 0.01 molar solution of calcium hydroxide is closest to which of the options? So try these, right, work through them, and then we're going to go through the answers in just a few minutes. Okay. Most. So I tried to give just a few hints for these first two questions. So the highest concentration of hydronium ions, hydronium is H3O+. That's the same as H+. So the highest concentration of hydronium ions, the most H+, means the most acidic. So think about based on pH, which is most acidic. Well, hopefully you picked A. The lowest pH, right? Lowest pH is most acidic. So A is the answer for number 1, because the highest concentration of hydronium ions, the most H+ is going to be the most acidic. And then which solution is the most basic? So I said the most basic is the one that has the most OH-, right? Or we can think about it as the highest concentration of OH- is the most basic. Highest concentration of OH- is the most basic. Now you might look at this and say, well, they're all the same concentration. Well, you're right, they are. But go through and start by labeling strong acid, strong base, weak acid, weak base. CaOH2 is a strong base. Right, it has hydroxide, it's a base. Ca is part of the B on the periodic table. It's a strong base. KOH. OH tells me it's a base. K+ is part of the B on the periodic table, so that's a strong base. H2O, that's neutral. Right? H2O is always neutral. HCl, hydrochloric acid, that's a strong acid. So based on what we did here, I'm going to eliminate C and D because we have a neutral and a strong acid. So obviously my strong bases are going to be more basic. But now we have to figure out based on two strong bases, calcium hydroxide and KOH. You think back to the do now that we did last week, where we had two strong bases. Well, notice how calcium hydroxide has twice as many OH-. So if we think about the OH- concentration for the two of these, calcium hydroxide is 0.2 molar. That means that the OH- is twice as much, 0.40 molar for calcium hydroxide. KOH is a strong base. It's a 1-to-1, right? For every 1 KOH, there's 1 OH-. So the most basic is the one that has the highest concentration of hydroxide ions. That's answer A. And then finally, the third one, the pH of a 0.01 molar solution of calcium hydroxide. Well, we just labeled this, right? It's a base because of OH. It's a strong base. Think about what it means to be a strong base. Even though this is a strong calculation, it still helps to show the dissociation equation. So it still helps to show calcium hydroxide with a single arrow to Ca2 plus and 2 OH minuses. An equation always helps. An equation always helps. So if this is 0.010 molar, think about what that means. There's twice as many OH minuses. Right, so if I do like this, 2 OH minus for 1 calcium hydroxide, there's 0.020 molar OH minus. Now, before I do a calculation, let's look at our answer choices over here. Or before I do a calculation, let's look over here. This is a strong base. Think about where the pH should fall if it's a base. Any base should fall above 7. Right? If it's a base, the pH should be greater than 7. I'm going to eliminate A and B. We have a 50-50 shot now. Now I want you to think about this. If I take the negative log of 0.020, that's the OH minus concentration. What are we finding? Finding POH. So negative log of 0.02 is 1.70. Notice what I labeled this. Please label everything. I can't tell you how many people choose B. We already eliminated B. That can't be an answer. It's not an option. That's because this is POH. The question wants pH. 14 minus 1.7, 12.3. 12.3 is closest to 12. So this looked at strong acids, strong bases, what they are, what they look like at the particle level, and how we can do some calculations with them. Yes, questions? Mike, what are your questions?
So for number 2, when we were comparing, what was it, CaOH2 and then something else with OH?
Yeah.
So if it was like, if like the one with 2 OHs, if it was like 0.02 molar and the one with only 1 OH, if that was like 0.04 molar, would they have the same pH?
Yes, they would.
So how would you, so they just both be the same amount of basic?
It would both be the same amount. Yep.
Okay.
Yeah.
And if it was like an open-ended question and it was asking for the pH like that and it gave you 0.010 molar, would we put the pH in 3 decimal points in?
For 0.01. So that's still just 2 significant figures. Because this just the 1 and the 0 are significant.
Okay.
The leading zeros are never significant, so that would still be 2 sig figs. So your answer would actually be 12.30. Since this was multiple choice, it was just whichever one was closer. But yeah, if this were free response, and if you did 3 decimal places, they wouldn't take off for it.
Okay.
So that's not something to super worry about. But yeah, you would be able to do 12.30.
Okay, thanks.
Yeah, you're welcome. H2O is neutral because H2O is a neutral solution, right? Water is our definition of a neutral solution. So water at any temperature, that's all our gauge for what is neutral. Any other questions? I'm going to copy this and put the other Google Meet link. If you want to get onto the weak acid, weak base, I have different links for it because I created them in